That's flashy. So I'm Pete Kirkpatrick. I'm the hardware architect for Pure Storage. I've met a lot of you guys before. And you'll catch me probably giving some sessions that have a lot more glitter in some of the main stage things. But today I wanted to be able to talk to you guys directly about how this stuff really works. And so we'll talk about the FlashArray X. But mostly we're going to focus on the technology that's really underlying that architecture. So the FlashArray X was launched about a month ago. Several of you guys were there with us to do that launch. And so now this is in production. It's out in the field. Happy customers, and people are really enjoying the benefits. And before we dive into it, I really want to I want to emphasize that this isn't like a tier 0 kind of product. It's not that we went after performance and with the goal of, cost is no object or sacrifice any of our other features. This is just a flash array. And it's just a little bit faster than luckily it's a lot faster than the old flash array. But it carries along all the same benefits. It's got all the same features, everything including active cluster. And one of the things that we really focus on, that most of you know by now, is non-disruptive upgrade. And so everything that's been done in FlashArray before can transition into the FlashArray X, and it'll transition out again in the future. So we like to think of the data as the array, and all this hardware and software that we like to talk about, it's kind of coming and going over time. But the data is really what matters here. Okay, so this is going to be extremely complicated. And so we're going to use very simple pictures instead. So really what I want to do is jump back in time a couple of steps, because you guys have all seen this before. This isn't new. This is the FlashArray M. And we started this design a little over 4 years ago. It's been on the market for about 3 years. But at the time, we thought that we had a job to do, which was to kind of repackage the components that were already present in the flash array that were essentially off the shelf. So we had to put 2 servers in this thing, and then a storage shelf, all in one box. Okay, so that was straightforward enough. But at that time, the product line was all based on SAS technology. And so we built everything ready for SAS. All the flash modules that you can see in place here are SAS-based. But we also saw at that time that we thought in the future NVMe would be an important thing. And at that time it was just that, it was a bet, because it wasn't important at the time. But we decided to sit down and build NVMe throughout the system. Again, placing this bet that a future would come where we really want to be able to put off-the-shelf NVMe drives, or we might want to do something special ourselves with that technology. The other thing we did at the time was we actually did have a critical bottleneck that was already limiting the performance of the system. So previously the flash array used SAS-based SSDs, and we did something like 99% over-provisioned SSDs to make them behave really well, because we didn't need a lot of capacity, we just need that great performance characteristic. This NVRAM, we really wanted to take that bottleneck and move it 10 years into the future. So I'm happy to say we haven't hit this bottleneck yet, but a lot of hardware is just kind of managing which bottlenecks are coming up next and then knocking those down one at a time. So we chose to use DRAM media for this NVRAM, and we chose to connect it to the controllers via NVMe. And really what that did is it brought this real benefit of NVMe, which is low latency and high throughput in the protocol, to the minimal latency media. And that gives the array this really beautiful write characteristic, where we can maintain a very, very low latency all the way up until the thing is saturated. So these modules do about 10 times the throughput that their predecessors did at much lower latency. And so we were able to create this kind of textbook ideal device for our write buffer. And we've been shipping that for years now, and we have the back end supported by our SAS flash modules, and life has been pretty good. But we want to know, how can we take it to the next level? So we're now replacing the SSDs with a similar technology, and these are going to be the generation of all NVMe flash modules. And those are the things we call the DirectFlash modules. So we brought one because it's always fun to look and touch. I like to point out to people that the red boards that we use there, those are what we call our P1 prototypes. And really red means don't ever ship this into the field. So luckily that's about 3 prototypes ago, and we're now into green boards, which you should expect to see in your systems. And I like to tell people, if you ever get a red board in your data center, like, I'll give you my personal phone number, like call me up and I'll come get it and we'll swap it out for something a little more stable. Okay, so I'll explain all the cool, complicated stuff we're working on. There's a lot of stuff going on underneath, but really you can actually see how this thing works. Is the orange handles make it go a lot faster. Okay, sorry. What we're really going to do is spend time, I'll try to spend most of my time diving into why this is a problem, why we had a problem before, and what we're doing about it. So we'll take a step back, and I'm going to talk about the limitations of conventional SSDs. And I think the refreshing thing is, 5 years ago, or maybe even 10 years ago, we were out saying, hey, look, the world is going to start using SSDs. And everybody looked at us a little funny. And 5 years ago, we were able to say, hey, we've corrected the economics, so now that you can use SSDs, but you can use it in a more economical fashion than you could hard drives. So now you have the best of both worlds. You have performance and economics, and we've never looked back. But now we're starting to see SSDs actually go down a similar path that hard drives went down. So if what happened over history was hard drives got bigger and bigger and bigger, and the technology was amazing to make larger drives, but we couldn't access them any faster. The latency wasn't dropping and the throughput wasn't going up. And so SSDs are now at risk of following that same path, where we can end up seeing these massive systems built with racks and racks of SSDs just to keep up with the controllers. And so we sat down and we said, what could we do if we get rid of all that legacy? What if we take all that legacy out of the system and we finally connect flash to software directly, because we own both ends of that system? So the traditional SSD is really limited by this disk legacy internally and externally. Internally, what the device needs to do is present the hard drive characteristic, which is this large contiguous address space, but it has to allow random overwrites throughout that space. And it actually does that at very fine granularity. We talk about sector size, even though people don't really use sectors as small as 512 bytes anymore, it's really allowed. But flash media doesn't work that way. It's actually completely different. So flash is built from large blocks. They're quite large and actually are the parameter within flash that's starting to grow every generation. And it turns out with TLC flash, blocks got bigger. With 3D flash, blocks got bigger. Now when they scale 3D flash, adding layers tends to grow blocks bigger. So we're getting into 16, 32, 64 megabyte blocks in flash, and that's going up. That's going to continue to go up into the hundreds of megabytes of capacity blocks down here. And we're still doing these kind of random overwrites at the front end. It just doesn't make any sense. So what the SSD does to kind of bridge that gap is it runs the flash translation layer. And that's really this mapping between this logical space and this physical space. It's funny because a lot of software people call the first one the physical space, but everybody just calls the thing below them physical, right? And we keep going down in layers. So flash translation layer requires garbage collection to reclaim overwritten space, repack it with new front-end user rights, and keep the drive going. But it also causes a lot of limitations. So the excess writes that are going on there, they limit the writes that you can do from the front end. They limit the writes that the user can do. They destroy the latency distribution on the read side as well, because you want to read data. If you're writing to anywhere close to that data, you're going to be blocked behind the write. If you're unlucky enough to get blocked behind an erase, you're going to be out, 5 milliseconds, 10 milliseconds before you can get data. That's starting to look like hard drives again. The extra writes also cause excess wear on the flash. And wear's a funny thing, because every engineer is really paranoid about their drives wearing out. And in practice, you really find out that they don't really wear out that bad. And the era of SLC flash we didn't really worry about it that much. And then MLC came along, and we were worried, and we found out if you take care of the flash well, it's going to be okay. Now with TLC, we had the same fears, and what's different now is it's always been more than enough. And now we're getting into this era where there's just barely enough endurance available to make a robust and economic system. And so this wear, this extra wear that's going on inside the drive due to garbage collection is starting to eat into that just barely enough that we have, and it's going to become more and more of a problem. We're looking forward to QLC now, and or some of us are, I guess. And it's going to be ridiculous. You know, you're going to be able to barely touch the stuff without wearing it out. And so this is going to become more and more important. And then, as everybody knows, this garbage collection needs over-provisioned capacity to do the job underneath, right? And so it's anywhere from 7 to 35% of the capacity is hidden away. We can't use it. Our users can't use it. This function is running internally to the drive is using that. And all of these kind of effects are really building up and limiting the application and the potential of an SSD. And then just to touch on, you know, that's kind of the main sort of source of complexity is this hard drive emulation that's going on inside. But all this stuff that's built up outside, and this is a very technical, this is a very accurate view of what that looks like, by the way. But the SCSI stack, the SAS interface, SATA drives, they were all developed assuming that the media had high latency. So why not serialize things and let them queue up while they're waiting to be serviced by this high latency media? And at the time, that was a rounding error on the total latency. But now that we have much lower latency media, all of this stuff is starting to also become a serious burden on the system. Okay, so that was history lesson. I know everybody knows that, but it's good to kind of establish, you know, what do we see as the problem? And this is our solution. We call DirectFlash. And this was kind of born of the recognition that we have a system. We understand the data flow throughout the system. We have highly parallelized software that's able to run on these many, many core CPUs. And we have high parallelism down in the flash with literally thousands of die available to do work. And so we thought, let's just get all of that stuff out of the way. Let's get all the serialization out of the way and connect everything from bottom to top in the most parallel manner possible. So we already have purity software that's designed to be flash friendly. So we recognize that the geometry of flash being this kind of large block format, and that once that block is erased, it's erased, and it can only be written once. We developed Purity to have large block-based data structures, and those data structures are immutable. So once they're written down forever. The other thing that it has is this inherent parallelism. So it's very, very easy for us to adjust the parallelism of the system to relieve bottlenecks. And so we're kind of set up from the software point of view for this problem to kind of work itself out. But from the bottom up is where we had problems from the SSDs, and we really wanted to take a big step forward.
Pete, the reason you don't have garbage collection is because you're writing a full block in a whack?
That's right.
So you never actually have to move data from that block to someplace else?
There's never anything moved within the drive. And then once a block is written down from software, we never override it again.
As each new technology comes along, QLC, you said the blocks are becoming larger and larger, and you're going to be able to maintain that?
Yeah. QLC is going to give us a different characteristic. The media is going to slow down. It's going to have this worse wear out characteristic. And we'll apply all these techniques to just maximize the benefit. Let's stay out of the way and not add any extra latency if we can. Let's maintain that through the whole stack so we don't have resource contention. Let's not wear it out any faster than we need to, and those really are the best things for economics and for performance. Yes. And so on the right side, the NVRAM is a nice buffer, literally a buffer that protects us from, it allows us to do all this work at our leisure, which is nice. Okay, so when we started to sit down and design hardware, again, we were making this bet on NVMe, but it really is the right starting point for a drive. You're not going to start a new architecture based on these legacy disk technologies. And we'll talk about NVMe elsewhere, and you've probably heard a lot of it before, but it's a very simple, it's very efficient protocol. It provides extremely low latency, very, very high throughput, and then this massive degree of parallelism throughout the system. It allows us to work around any resource contention that we might run into. What we did was, on top of NVMe, is from the DirectFlash module, we present an API to software. So that software has this really granular view of the geometry and the topology of the flash underneath. And that allows it to do very exact data placement of the data structures that we've developed at the data management level, write them to flash in a very precise manner, and then to schedule operations very precisely so that we can avoid resource contention. So for example, if we know that one die is busy doing a write at this point, and the data that we want is on the same die, we're not going to queue a write to that die and wait 2 milliseconds for the write to complete. We're going to immediately, we have this a priori knowledge about what resources are busy and how they block each other. We're going to go get that read from a higher level mechanism in the system. We have of course, other ways to rebuild around writes and things. And so this is really the ability for us to schedule and use the flash very, very efficiently. So no FTL is required at all. There's no GC. And so we can use all of the resources here for both performance and capacity in a much more efficient manner. So of course, we get the converse of all these things that we were working around in SSDs.
Is that it still exists, it's just at a higher level?
Yes. So of course, we're doing garbage collection already in Purity. We're just not going to waste our time and do it in the drive anymore. A lot of times, Purity is actually fighting the drive to get the work done. And now we just remove that lower layer, eliminate it from the drive completely, and we just get a lot more streamlined access.
So if I was looking at the cost, and the cost of you developing, building, and continuing to evolve that technology, compared to the cost of buying an SSD, compared to the cost of buying an NVMe SSD,
Right.
how much cheaper are you doing yours than you could do if you went the other way? Assuming we didn't get the performance, all the other performance benefit characteristics. Purely on the economics, why is it better?
So the NAND and the SSD market's pretty dynamic. You'll even see sometimes NAND and SSDs, one rising above the other in price. So this gives us another degree of freedom to optimize. We can still use commodity SSDs. We can plug SATA, SAS, or NVMe drives in here. And we're constantly qualifying new drives, and we want to always keep that process refreshing. This is going to give us a different degree of freedom to get more efficient on the use of the flash that's underlying it, and of course, get the higher performance. Again, I can't emphasize that enough out of efficiency. The most basic way you should look at cost savings is the amount of over-provisioning that we've eliminated. We use that within the system to give the system an overall more efficient performance, and then we share some of that directly with the user. So that's like a direct benefit that we can pass on. Of course. Like we currently do, we attach SATA drives, but we could use any SATA drive, any SAS drive, any NVMe drive. As long as NVMe needs to be dual ported, SAS would need to be dual ported. So I should point out, you can plug any drive into the system. You can't use any drive in this manner. This is the DirectFlash technology that we've developed the hardware and software together. But you can plug any NVMe drive into the system and get some of the benefits. What you'll find is you get the benefits of the NVMe interface and not the benefits of DirectFlash, which turn out to be, another order of magnitude bigger. So we end up with high sustained throughput, especially on writes. We get this very low deterministic latency, and that's focused on reads. No over-provisioning, so we're saving, for a performance drive, if somebody's going after a high-performance NVMe type drive, they're going to be in that 35 or more % over-provisioning camp, just to try to get the sustained performance up. And we're just going to kill that completely. And then we're also extending the flash endurance.
So if you know the architecture of the drive, things like writing to a block, something you already know if it's a standard SSD. Why not just get the vendor to turn off some of the features and just use standard?
So we've worked with all our vendors on a similar thing. I think that eventually that's gonna happen. But what they have to do is satisfy the needs of the entire market. And over the next several years, they'll figure out what the needs of the entire market are and finally satisfy it.
But that's an easy thing for them just to give you a switch. That just says switch that feature off. Switch off garbage collection because you're not.
In concept, it's that simple. In practice, it's turned out to be really hard. And we do expose a lot of detail. The API is actually quite simple, but the level of detail that we expose through the API is very, very rich. And they don't really want to give us that much detail about what's going on inside. But we have visibility down to every block of flash. We get detailed statistics on every read, every write. We know how long things are taking, we know error levels, and we can really use that information to kind of enhance the data placement and all the optimization of the scheduling and things. So I do think eventually what you're saying will be true. It'll just take the industry a long time to get there. Okay, so now we've got DirectFlash. We put it into FlashArray X. And it's nice to point out that because we've solved a lot of these problems, we can now make very large SSDs. And the flash module you have there is 18.3 terabytes. So if you put 20 of those in a system, you're going to have over 360 terabytes raw. We like a factor of 3 if we account for RAID and system overhead, but then we add back kind of our typical data reduction. This is a petabyte of usable flash in 3RU. So we can get extremely dense with this, and that's just awesome. But not everybody wants to buy a petabyte at a time. And so a lot of customers are going to say, well, look, I only have the need for 20 terabytes right now, and I really want to be able to expand. We could fit 20 terabytes in half of this system, leave the other half open. They can buy another data pack, and now they're at 40, but their needs may keep growing. And so everybody knows what a shelf is for. We thought, let's just keep extending the benefits that we've developed in the DirectFlash modules and extend them all the way out throughout the back end of our system. So that's the DirectFlash shelf. And so FlashArray X is 2 months old, a month or so is launched, but the DirectFlash shelf is the new news that we'll talk about here at Accelerate. And I do think, if you've thought through this, it wouldn't be a big surprise where we were headed with this. We just didn't have it all done at the same time. So what a shelf is for is fairly obvious. We can either use it to get bigger and bigger capacity, or we could use it to start small and keep growing incrementally. But what's interesting here is, how does this thing work? And so we've got all NVMe in the base chassis. We've got all NVMe in the expansion shelf. And an approach that's been tried in the past is to connect the two with PCI Express. And if any of you have experience with systems that are built with PCI Express externally, you probably don't do that anymore, and you probably had a very frustrating period of your life. But if you build this with PCI Express and that cable goes down, you're gonna have a bad day. So the error handling that happens with this many devices, and of course we could have several shelves, this many devices lost to an operating system all at one time can be a fairly disruptive affair. And so we're using a different technology here, and you'll see this theme start to repeat itself over and over and over. But NVMe over Fabrics is a new standard. It's put out by the same standard body as the NVMe standard was originally, and it's following the same themes. It's a simple spec. It's easy to understand, but it's also very complete at the same time, and it extends those basic benefits of NVMe onto the network. So low latency, high throughput, very high parallelism. And in this case, you also get another benefit, which is probably underappreciated, I guess, in my opinion, is you can implement NVMe over Fabrics over different fabrics, but we've chosen to use RoCE. And so that's RDMA over converged Ethernet. So these links, they're just Ethernet. But at either end, we have RDMA technology. And this is very well understood. It's used by all sorts of different systems. And it's recently gained a lot of adoption in cloud infrastructure, really because it's offloading the CPU from doing data movement. So data that would have had been moved over regular Ethernet is now offloaded to the RDMA function. And we get this extremely efficient transfer of data between the two systems. And then it also maintains that idea of parallelism throughout, because Rocky and RDMA is built on a many queue model. So now we have many CPU cores, NVMe to many queues down to SSDs. And the parallel here is we have many CPU cores with many queues through the RDMA connection to many SSDs and the many die we have down below. So again, you can just see us repeating this theme over and over. We're going after every bottleneck in the system, anywhere we could have resource contention, anywhere we have locks, anywhere where we have blocking access, and we're just eliminating that and going as widely parallel as we can.
So presumably you could build out a mesh.
What's that?
Presumably you could build out a mesh of controllers.
You sure could. So today what we're doing is this very simple point-to-point, and you start to get my theme, I oversimplify things a lot. This is just to think about chains. We would chain these as our back-end shelves. But the next thing you're going to want to do is to start to connect to the rest of the world, right? And really you can start to build really interesting topologies with this. But we're going to take the main benefits that we've developed throughout the whole system now. We've got this extreme degree of parallelism within the storage portion. And now we're going to expose that all the way up to applications. And this is not a product. This is what we're calling a technology demonstration, but we're doing it here this week at the show. Cisco's been working with us, and we've got a UCS connected through their fabric to the FlashArray using NVMe over Fabric's technology, and then we're serving data back to that UCS. So this is a little bit of a peek into the future. But again, I love to repeat myself, but now we've got this low latency, high throughput access all the way from the CPUs where applications are running through the entire SAN, or you may not call this a SAN anymore, but all the way through the network to the array, all the way down through storage in every aspect. And that's really what we're excited about, is really unlocking all of the potential that's been bound up in all this legacy and causing too much resource contention for us to really take advantage of the entire infrastructure. And I think that's it. So that's what we've got.
Go back a slide. So the shelf.
Yes.
What are the 8 slots at the top? Are those flash modules or are those NVRAM?
Yeah, good point. So you can see that there's a little bit of similarity here. And when we originally did this, it wasn't an accident that these were exactly the size of 2 modules. So this is essentially the same chassis. It's like 95% the same. But we did want to break these out into just 2 regular slots. And so all of the slots here are the same. They all hold DirectFlash modules. So this is essentially a 28 drive shelf.
Okay, and it acts as a JBUF?
It's basically a JBUF on behalf of this part of the array. The smarts are still up here.
Is the connection 40 or 100 gig Ethernet?
These are 50 gig Ethernet. And of course, I oversimplified, but they're HA and multipath. That's not stuff that you'll find standardized quite yet. And so we had to go a little bit out in front and get some of that to work. And then the other cool thing is, the way we terminate the protocol inside the shelf is actually on, of course we have RDMA, but we also have a CPU there. Today the CPU is pretty lonely, and it doesn't have all that much to do because it kind of shuffles pointers between NVMe over Fabrics and NVMe devices. But it's a CPU. And so now we've got a way to put a lot more horsepower and to put more cores into the system.
Is the NVRAM only located in the controller?
Yeah. So the NVRAM really needs to be sized to cover round-trip latency to storage versus the front-end bandwidth of the system. And so we like that to be sized to kind of match with the controllers. These guys are telling me I'll take more, but these guys will cut me off at some point. So initially, we're going to start with attaching 1 shelf. And again, if you count 4 48 drives times 18 terabytes. You can get to extremely large system that way. And then we're gonna, as the product line develops, we're gonna allow attaching more chains and deeper chains, and you'll see a lot of history repeat itself that way.